Okay, we'll start now. Good morning. Today, what we will see now is a demo how we can divide, how we can translate a algorithm to RTL. Since all of us have sometime been got an exposure of writing some codes, and the way we write software code is quite different the way we write an RTL. So we will try to see today how we can map the style which we write in a software and try to synthesize an RTL. So RTL is register transfer level, is in which how we try to manipulate the registers to implement a digital system. So one way is to use a separate data path and control path. So we'll start with the motivation that why we want this to have it. So even if it's not very clear now, but after going through the tutorial and it will be clear to those who are seeing this for the first time. So the motivation is in the to have a very good architectural clarity. So when we have a data path and control path, the data take care of all the computation, data movement. So in digital, we implement it through ALU, register, mark shifter, and control is the FSM. So what and when we separate it out. So the advantage what we get is we can document a very clear microarchitecture level. So this is all used in a processor design as well as we have a lot of configurability. You can visit this again later as well. The second thing is the advantage is in debugging verification as well. If we separate out the data and control path, we can verify it quite easily. And the tools are really good in doing all this verification for the data path and control path. So we can localize the issue, whether it is in the FSM or whether it is in the data path. So this helps in debugging as well. Implementation wise, since we are segregating these two, it helps us to reuse our existing data path controller. We can play with a lot of different controllers for the same data path and or vice versa. It helps us to scalability as well. Also, when you work in a team, you can divide the work easily. Uh, if one person is working completely, it's difficult to work on a complex project. So in that case, this division helps us to divide the work as well. And it's also tool friendliness. So just for brief motivation, we'll start with how we can start thinking about this. So let's take a design problem. Suppose if we want to make a ECG peak detection circuit in hardware. If anyone has any question, they can ask in between as well. So suppose what you see now is an analog signal. It's an ECG signal, and how we can detect the peak. So first thing we need is, since we all are working on digital, we need to digitize it. So one way is like we take this analog signal, we have an ADC which will sample it. So this all cross points are the sample points. Now in these sample points, if we want to find the peak, so this is something we will try to implement today. See how we can find. So we can reformulate the problem as like we read five 8-bit numbers serially and find out the largest number among them. This can be our design problem. Why five numbers? So it's a small number for demo, for simulation, it would be easy, but we can scale it to any numbers. So first thing that is important is what are the interfaces we will need. So if we have five 8-bit numbers, so we need to find the largest number, so we need to tell back to the environment that, okay, these are the numbers. This is the number which is has the highest value. So we need a data in. So serially we'll get 5. We need data out that will give us the max number. Done is just to tell that we are ready now. And these two, reset and clock, are it's more like a global signal. It will go through both the data and control path. Okay, with this in mind, how we can implement finding a max number in hardware. So in software, if someone tells us to write, so one way is you need a num variable where you will store the number sequentially, which is coming in data in. Just to recap, data in is the number which is coming sequentially. Data out is the maximum number we will give out, and done is the decision. So we need, at least we need num register or variable to store that number that is coming sequentially. We need max, which will store the maximum. We need count to count that whether we have reached those 5 numbers or not. And then we have done, which tells us, okay, now we are, the max number is the right number. So we can have a loop where we sequentially take the data into the num variable and check with the max. Since we kept max 0, any number greater than 0 will now take that max, will get updated to the max. So now this goes, num will load to max, and whenever it's the new number is smaller, max will retain itself, and we will update the counter, and we will move this 5 times. And when this loops end, we store the max, and when then we raise and assert Boolean logic done. So this will communicate to the outer system that, okay, now we have the max number. So so this is a typical algorithm which we write in C, and now how we can translate it to the hardware. So first thing, before going to hardware, a digital system, a quite common digital system, has some registers. So since we need to reset our registers so that the output gets 0, and we don't want to update this number in every clock. We want only when we give an enable signal. So enable and reset are the two controls. And this is a flip-flop which stores a number. So just keep this in mind that all in our register, wherever we tell that we're talking about register, we have enable, reset, and clock as control signal, and this input is and output are data. So now we'll see how we can map that what we have seen now as a pseudo C code to hardware. So we saw that we have a num variable in our C code. So in hardware, we need a num register. So we have a enable, reset, and clock. So this enable and reset is coming from outside, clock is also coming from. Enable is something which will be generated by the FSM, that is our control path. So we will come to see the, when we see the control path, just to make sure the color combination, I think I missed it. So this green color are something which coming from outside. Clock, we make it special because we need, when we write some constraints in our FPGA, or or we use an ASIC design flow, we have to take care about the clock. Overall, these are coming from outside the system. And anything which is generated by FSM, we will, it is mentioned in blue color. Anything which is coming from the data path it's in red. So keeping this color combination, we see that the green color, which is coming from outside the system, will go to the register enable. And why we have this num, we see that num has been updated twice. One, it is by 0, one it is when we have some data incoming from outside. So similarly, this reset helps us to make it 0, and this num, the data which is coming out, we can connect like that. Second, if we see the mux, again we have 0, but mux is updated twice. One, mux is updated by the num variable, and the second time mux is not updated. So since it is updated twice, so we cannot connect directly to a register like this. So we need a mux here. If suppose in an algorithm we have a variable which is updated 4 times, so we in that case we would use 4:1 mux. In our case, 2:1 mux is enough. And these wirings are something which we need to do it when we implement a data path. Now count is equal to count plus 1. So we need a count register which will get updated by count plus 1. So we need an adder which will take so okay, we need an adder which will add 1 to it, and this output will get updated to the count. So if you see the input to this count register, we have the added value of count. Now comes out max. So whatever max variable we have, that goes to the output. So this is we need, and now comes to a comparison block, that is the max less than num. For that, we will take a comparator, will take a num register output, will take the max register output, we will compare it and put it back uh, to control the mux. Because here we can update. Then we need one more comparator which compares as whether we have the total count as 5. So if we have more number of data points, so we can update it accordingly. So this makes our data path where we have all our arithmetic combinational circuit logic. Now comes the implementation of the control path. So the same code which we have seen now uh, in the data path, see what was we want to implement. Now it is when we want to implement the same C language, the C code. We can divide it into various different states. So in the reset state, we have we make this all this num max count variable into reset state. And here this green is same as the color which is going to outside the system, and resets will go to the data path. And when it comes for updating the number, we will have this store state. So when we are in store state, we will only enable the num, so that whatever there is in the data will get stored in the num register. Now comes our comparison state, in which we will just enable the max, so that based on the value in the data path, the max it will get updated. The mux will help us to take the decision. Now the counter, and then we will loop it. So we will loop this, um, we'll go from loop to store till our count is not is equal to 5. Once we reach that, we will assert done state, in which we will enable the max output a register, and we will be done. So here in the control path, we are focused mainly on when each step of the state we should keep. Now, if we see keep the both together, so we'll have one Verilog file in which we will have all the data path components. We'll have one in which we'll have all the control paths. So this is how the control will generate the enable signal, and sequentially in the right time we will get all the desired output. So now how this data path will get implemented in the code. So we need to implement a register num. So you can see here, so it's a generic register. We have used parameter. So it's good to implement this. It's always good to use parameter in the design. Is it makes it very easy to scale. So suppose tomorrow if you want to increase the number of bits, we can just simply change it while we call it. Here we can see that the way we make it 8 here or 10, 16, we will have 16 registers altogether. Um, and one thing, when we write the data path and when we draw it on paper, we need to give some net names. So if you say these gray nets, so that when we use it in our Verilog code, we will use this net for stitching all these modules. So we will see that we will have these nums, comparator, max, out, count, adders, all implemented separately in a separate Verilog file. And one data path file will have all this stitching. So this is a snippet of a code. It's not a complete code, which we'll see later, but it's just to show that what we need to do when we write the data path code. When it comes to FSM, there are various ways to implement the FSM. Three always block we can use, or three process in terms of in in VHDL we have process. So it is like we can implement either in one process, two process, three process implementation we can do. So here we will do a three block FSM implementation. There is a quite advantage of doing this is we have separate, this is the way how FSM is implemented. You can refer any book, but just we'll go briefly over it. So there are three blocks. One block is next state logic. It's a pure combinational block. Like based on what condition the state will change. One is the state register. So in this case, we have 6 states. So we need at least 3 flip-flops to implement these 6 states. So this takes care by the state register. Now one block, the output, it can be combinational or sequential. In our case, it's all combinational block. Let's see a snippet of it. So, uh, so this the code I will share. You can use it as a template. So you can implement it any algorithm. Just if you can make an FSM, if you make a data path, then that's a simply you can translate it to to these codes which I'll share. So here just to see that how we can determine the next state logic. If you see the reset decides that if we need to go from reset state to store state. So you can say that here the reset, if we put if condition, next state will be reset. If else, then next all these states will go. Especially to mention is the loop state. It depends on a equal to b and a equal to b bar. So based on that, we decide whether we need to go to the done state or store state. And state registers are simply implemented as a flip-flops. Now comes the output logic. Now we have seen in the next state at what input we are changing. Now for output logic, it's state dependent. Like when we are done state, it should assert done. When we are in reset state, we should enable, we should have reset num max count as one. So this is something which we implement at the output. It's a pure combinational logic. If you want to avoid to make it synthesizable, if you want to avoid to have a latch, it's better by default use all state as 0, so that every time we have mentioned it 0, and based on state we will only make the one which we need to enable as 1. So in this way you don't have to write if else, multiple if else, um, and it will always generate a combinational logic without a latch. So this template is some best practices in which you can in first go have a synthesizable code. One thing again for mention to the loop, it based on the input, it generates a separate output. If we go here, it should enable the out. For the other state, there is no, so we don't have any. Now we can, one thing which you didn't cover in this is handshake. We have assumed that when reset is low, we will take the number from outside, but this is not the case. However, we'll come back just to see in Verilog. So why we have used Vivado for this is you can run your simulation, you can synthesize your design. So this is quite helpful. So that is why we have used Vivado. So when you create a project, the you can add all the design files. So in our case, what are the design files? So I have added the data path.v. This is the data path in which we have stitched all the registers, and so we have one register. Okay, I can show you. Let me make it better. Okay, so this is the data path, and if I keep this data path here, so we are trying to include all the register, comparator, adder, and how we are doing it is so we have a separate register Verilog file for register n. N is for n bits, any register for n bit. Then we have one adder, we have comparator, and we have mux, and we have another second comparator. So these are the ports A, B. In comparator, we can in this we have three output if is A less than B equal to B greater than B. So we have used all those nets to stitch it. And if we go inside, I can just show one. So this is how a register is implemented. One positive, we have a reset. So it's a synchronous reset and also enabled. Similarly, adder, it's a standard. Um, so the data path is quite well optimized in the tool. So just by doing and based on it will try to implement it internally, whether ripple carry or carry look ahead, depending on what speed requirement we want. Similarly, we have a comparator block. We have this mux 2:1 mux, and this comparator is exactly similar. So this is how we see the data path and the control. We have clock reset done, which is coming from which we need to communicate to outside world. And just if you want to have a glimpse, so this is something we are implemented here. So these signals are going to the data path enables. So this is how we implement a state decoding. So we need 6 states. So we encoded it as 0, 1, 2, 3, 5. And this was the next state logic. And this is our state registers. And this is the output logic. So, uh, so if anything, if you have implemented on paper, can be easily implemented, can be translated to this Verilog code. So I will run elaborate. Elaborate is a process. We have this in ASIC design flow as well. The first thing it does is it maps whatever we have written now to a generic gate. So it's not a physical gate. It tries to map it. So here you can see that whether there are some latches which is created or some mistaken logic has been done. So this is something which the tool has done. Both Genus does in ASIC flow and Vivado does here. So this is the register counter uh, and adder, and this is 1 bit. Okay, I can show. So this part is exactly what is synthesized, what we have made as this part. And the count, we have a comparator, which we can see here as a comparator. Similarly, we have all this num going to comparator, mux, and max register going to output. So same thing, that path has been generated, elaborated like that. Similarly, in the um, so this is this register. This is how we generate the next state logic, and this is how the output logic is generated, and based on that you see the different time it communicates with the data path. So these two, how it is stitched, if so there is also top V, where at the top level we have this data path, we connect some signal, we have some control path, we connect some signal. So this is the first thing which we saw in the beginning, how, so this is the data and control, and these are those signals which is going. So going back to the schematic, yes. So these are these signals which are connecting from control to data, data to control, and some data in clock reset done. These are some outputs. So the what we can do is we can manually test each control path separately. Like in the tool, what we can do is we know that based on reset we change states. So externally we can apply a reset and see that whether we are going to this state or not, or if there is a bug in while there is a typo due to which we are not able to change the states. So this you can do easily. Separately you can test these two. So if you are working in a team, so one person can do all paperwork, uh, who will be in charge, make these two based on the algorithm, what is needed, and then two people can divide it and try to implement separately. So you can work in a team and there is a clear isolation. Um, I think simulation wise, we can run behavioral simulation. So I have added a test bench. What it does, it does all generates four data exactly where when reset is zero at the right time. If someone needs a demo, I can do a like manually how we can test the data part separately, how we can test the um, control part separately. But for now, if it's clear, if all of you have been in some way exposed to simulation, I think that is not needed. So just I will add these add to waves for to see all the waves here. We'll reset it and run. So let me show you this. So we have these number 2A, 7F, 10FF generated, and in the end, we will it will generate FF, and at the point done is there, and these numbers are sequentially given in, and we'll see now how we can do a better handshaking, and in that way, we will not. Okay, so what is remaining? I didn't show the test bench. So at the test bench, we just have these clock reset data in data out done coming from outside. We have this DUT, which which we apply this signal. We have this clock every 5 nanoseconds. It generates a clock. We have this number, sample numbers, then initialize it zero, then at every clock edge for 3 clock cycle we keep reset high, then we go through all the states, and in the end we can see that whether it pass or fail. So test bench design, we will not cover it because it requires a separate session for that. But this is some of the brief overview. And then if we synthesize this design, and when we run, we'll see the same. So it gives in first cut synthesizable design. So synthesis is running. So when When the synthesis run, we'll see that it will work properly after synthesis. So we'll go back. What we missed here, not missed, we didn't start was about handshaking, that how this block interact with outer world. We assume that whenever reset is 0, we have some number. That's why we straight away enable it. It will take that data. But in real system, we need to implement some type of handshaking. What we do is after reset, we will be in a wait state. Wait state is whether the data in which is coming from outside is ready or not. So this request acknowledge, we need two separate signal, and it's quite easy to implement. Just you need one extra state. Request acknowledgement will come from the outside, and then we will wait for whenever we are on wait state, we will raise a request signal. It's a Boolean logic. We will make it high, and once based on the acknowledgement coming from outer signal that okay, data is now ready. Just to show you how it works is um so so if this is the your top, you have this acknowledgement signal coming from a block and we send request. So with acknowledgement, we have also data in coming in. So this is one way to implement handshake. There are various ways you can implement. Suppose if you have an ADC, the ECG signal we started with, and you have this block, so your data is coming here. So also ADC generates a signal which we call it data ready, or so that can we can consider it as an acknowledged signal. Or in Nexus 7 FPGA boards, if you use the ADC, they call it strobe, that this is the right time to take the data out. So, so these are various ways, like it depends if it is an ADC or if it's a separate digital block. It can be a memory, it can be a FIFO. So how this data is coming in, it depends on your action. So this is something you get as a problem in your specification document. Okay, this is something coming from a memory or P4 ADC. You need to then think about these interfaces, and based on that, you can implement the controller. Implementation wise, if you can make this on a paper, then it's a simple translation. Okay, now we will go to some other things. So I when with these codes, it's better to do some hands-on mini project. So I have some suggestions, like you can take a ECG signal and make a heart rate counter. So what uh, to implement this, the same code what we have seen here is, so we have this ECG signal. At that time in this demo today, we have seen that we detect the peak. And if we want to calculate the heart rate, so this is called R signal in ECG. You need the index. So we can consider it as a time. So you need this and this information to calculate the heart rate. So one way is take an FPGA board, and in this FPGA board, AWG is an arbitrary waveform generator. Depending, if you can use a function generator, and you can apply a triangular wave also. If you don't have this arbitrary waveform generator, you can load a ECG signal continuously and changing the heart rate and use the ADC of the FPGA. Nexus 7 is one of a very, it's a cheap FPGA board which you can get. And here in the FPGA, you implement this heart rate counter and this ADC. Right. And you can, on the FPGA board, you have, if you have an FPGA board, we have LCD or 7-segment display, you can update it. update the heart rate in real time. This is some of the things you can do, and it will be a quite great learning. It's more like a swimming. Unless you are in water, you cannot learn swimming. Similarly, uh, if you want to learn about digital system design, you need to do some hands-on. Okay, so then you can implement data control path. You can have this. This is a something you can start with. It's not necessary you follow this. This is just for some pointers to do, and there will be some learning outcome if you do this project. Is like you will get a hands-on feeling of how you implement data control path. You'll learn about ADC interfacing with FPGAs, timing, handshaking, and you will get a continuous stream of data. Then you need to think about windowing. Like in the example we took, that we take 5 data points. So you need to, windowing is like continuous stream is coming, how much data points you need to take. And then all this complete system you can implement. Another project is more into like hierarchical RTL design. So how this is how a complex projects are made, in which suppose you have one RTL in which you have control path, data path. So this is a GCD. So if you see how to divide two divider, if you want to make 2 number divider, you need to do GCD, and this will again be inside. So this will be a part of a data path. You will have CP1 and DP1, and this will be CP2 and DP2. So this you can put it here. So this you will learn like how you can divide a complex algorithm. So in C language, if suppose you have a function, so you have function 1, and then you have bracket, and inside you have function 2. So this is how like you implement this separately and test it. So that's why this approach, you can, it's a modular approach. And then you use this. So a team can work on this, another team can work on this, and they can integrate and verify it quite effectively. So this, if someone wants to get some hands-on on hierarchical design, so this can be a good example in which you find GCD of 2 numbers, and then you have a divider and get a remainder and quotient. And this, if you want to do it on a FPGA demo, you can also try that. These are some outcomes you will have. So you'll have 2 FSM, 2 data paths. Some handshaking is required because this is somewhere you will get a feeling of how and handshaking is important and how it's implemented. This is one of a recent paper, which I will say that you can do a lot of ML inference in hardware. So this is from a research paper. Now, if you see this diagram, you can see that this is when, so everyone use a different notation, like this control unit exactly a control path or FSM, and these are our data path. If you see mux, one thing we didn't cover was memory. We had all registers, so sometimes you require to a very large storage, like 100 to hundreds of kilobytes. So it's not area efficient to use it to store it in a register. So for that, you will have a memory, the same memory block you can instantiate in your data path. You will have write enable clock, and this is data in coming from outside and data out. Um, so there are various ways in which you can implement memory. Some are in hardware like RAM. You sometimes you need ROM, and sometimes in FPGA you have LUT RAM. Also, sometimes you can implement FIFO. It depends totally on the requirement. So if you see this data path is this sigmoid and tan H LUT. It's a function. It's a CANH means you have some input here. If you give it to this block, it will generate you some output Y. So this generates it output, and these are registers, and these are just multiplier maps. So what we have seen today is the same thing which you have implemented can be used at various applications, ML inference, sequencing. In this same example, if you see that this is a one unit block, it goes to other. So this is where you can, after a bit of handshaking, you can see that how the same block can be interacted, and in the end you will get an output. So there's a long journey. So today just it was a glimpse of how we can start with a simple algorithm and implement it in hardware. Uh, okay, this is something I had for today. Is there any questions? No. Yeah, Sadam, yes.
Yes, sir. This so all these blue lines here, they are controlled by this control unit in this.
Okay. Can you repeat? Sorry, audio was not.
All these signals that
Yes.
are visible in blue lines, blue arrows,
Yes. Yes.
they are being controlled by the control unit.
Yes.
Is
Yes.
it correct?
Control unit. Yes. Yes. Control units generate all these blue lines, and
Okay.
also control unit takes some of these lines. So it will be very cluttered if you. It would be difficult to implement everything. So in the end, this diagram, um, if you see this diagram, these are some connections. In paper or in diagram, it's not possible to show everything. But yeah, it's true that there are something which is coming from outside. There are some blocks which is going in. And if I show you this, yeah, this one. So all these reset signals are going here. So whatever you saw in that ML inference one, it was right. So these signals are there. Also, there is a clock here. It's not mentioned. And yeah, yes. Anything else other than that?
Yes, no, no, sir, that was my question. And so this SPI initializer, so there is a control signal coming from outside as well. This SPI
Okay,
initializer, there is an
so
arrow coming from.
right. So this, so these are like SPI. Okay, so this memory needs some weights and bias, and how this memory will get updated. So this SPI initializer helps to update this memory. Okay, let me try to draw here. So what happens is in hardware, if we have a memory, let's assume it's a RAM. So it will be from 0. These are the address.
Uh, Sorry, sir, are you drawing something?
Yeah, can you not see the annotation?
Oh, sir, annotations are not visible.
In all of them, when I started from beginning,
Yes, sir, since the beginning.
so there was no annotation. You were not able to see any annotation.
No, 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 sir. That was one of I was thinking maybe you're trying drawing something, but it was not visible.
Okay, okay.
But
Sorry
at
for
my side, it is visible, I believe so, because I can see like Mirage sir actually writing something on paper. So I don't know whether some people can see, some people cannot see. I'm not sure.
okay, okay. So can you
Yes, sir,
see
is
now?
it visible? Huh? Yeah, yeah. Now, okay, it is visible for us. someone, but not for me. Maybe I have to
Okay,
turn
you
on.
you you can see on their screen.
Okay, yeah, yeah.
Okay. So what is so now this is the data path in which you have a memory, and now there are some numbers as a weight you need. So suppose if you are implementing an FIR filter, okay. So if you have an FIR filter, so you need a storage where you have H of n, right? So that when you have some signal coming X of n in hardware, then use this X of n and H of n, and there will be mainly MAC operation, and then you get the output Y of n. So once you're in your hardware, how you will upload this constant? So similarly in ML inference, you have weights in which you have these numbers like A1, A2, A3. So you need to load this. So this SPI initializer, what it does is at what address you need to update these numbers. So write enable, what it does is when you apply write enable, it it helps you to write. And when you go for this is clock and this is your data and this is the address. So whenever so in register there are no address, so it's a single register. But in RAM you have address. So if you see that address, data, clock, and write enable, these are quite signal to update it. And based on the control unit, then based on this address, when you update this address, you will get the output. So that weight can be then stored in a register sent for any MAC operation. Okay. Is this clear, Sada?
Yes, sir. Yes, sir.
So you will get a better understanding when you start. Don't jump directly to here. Start with a simple, just see the demo. I will share the script. So just see with that, try, run it, explore it, and then you can slowly move to at this stage. But for this, you need to know, you need to do some Python simulation and see how you calculate weights, and then you can implement and verify.
Yes, yes.
Okay. Anything else?
No, no, sir. Thank you. Thank
Where is this? So let's see. So when we so similarly after the design synthesis, this is something which Vivado gives you access, a free access to synthesizable tool. If even someone is working on ASIC design flow, you need a licensed Venus tool. But here, if you go ahead and just do layout post synthesis simulation. Same, if you go ahead and do implementation, you need to configure the IO pins and all. Then you can have a full implementation on hardware. It's not great. Yeah. But the synthesized netlist is now simulated. In this way, what I have seen is like even if you in some of the things may not be very clear, but try with one template and start doing some of the projects, simple, smaller ones. It will give you more confidence. Then you can build it on to a bit. Meanwhile, I'm running it. Anything else?
Sir, is this being recorded? I wanted to ask.
Yes, yes, it is recorded. I will share the link after.
Yes.
Uh, it's the same output we can see here we got after synthesis. Mm, Yes. So it's like a very good template for developing. One last thing I would should acknowledge my like professor who taught us digital design in IT Bombay, and whatever course I have put here, he taught everything in VHDL. I have just translated, but this style and approach that covered in this lectures was taught in our class. Okay, thank you. If okay, we can start. If if there are no further questions, if there is any feedback, positive, negative, or any suggestion or any topic which you would like, whenever we get time, we can make one more sessions like this.
Sir, maybe some like basic algorithm, if possible, is like machine learning basic algorithm like decision tree, like how we should uh,
Okay,
approach it.
okay. I'm also learning that maybe when I will be in a good stage, then I can have. But yeah, I would say signal processing algorithms. If you
Yes,
implement FIR filter, you will cover a lot of part of ML inference in that implementation because there are quite common requirements for that as well. But yeah, there is some extra we need to do for ML inference. Okay,
yes, sir.
may, whenever I'm ready or I will be able to deliver, then definitely I can try that.
Okay, yes, sir.
But there are
Thank
other
you.
things we can do is someone asked me once was like how to write a self-checking test benches and all those things. I have to work on it. If I get time, I can, or if I can share some codes if I get for the same time, whatever demo we had today, we can use to test that very efficiently.
Yes, sir.
Okay,
Sir,
okay,
there is
then.
one more question. Sorry,
Yes,
sorry.
yes.
Sir, is test bench also synthesized?
No, no. If you can see in this design, so we put all the files like if you see top.v and datapath.v reg and are all in the design source control path. And in simulation, we put test benches. If you put it here, it will not synthesize and you cannot see. So if you are using Vivado simulation flow, try to add. So just when you go here, add sources. Similarly, if you want, if you have any test bench, even without test bench, you can do and test this. If you are in a test bench, you just add it here and you need to select create simulation sources. Because it's not synthesizable, we put it separately.
So my question is again, like if let's say if you have a synthesizable net list after running this thing with the same
Mm,
test bench, then the
Yes,
synthesizable code also can be used with the same test bench. If the both the
yes,
output is same, then possibly
yes,
your code,
yes,
your
yes,
net list is almost same.
yes, yes, exactly. So this is why, so this is design source, and from here, if you see, we have post synthesis function timing simulation. Then we have post implementation when on FPGA fabric with routing, everything considered in this type of simulation. Yeah, so the same test bench can be used for behavioral simulation, post synthesis, post implementation. Okay, then we will stop here. Thank you everyone for attending.